Hello, students, and welcome. Today, we're going to tackle a very important topic from your Solutions chapter, colligative properties. Don't worry, in this short explainer, we will make it so simple that you'll remember it perfectly for your exams. So let's begin.
First, let's start with a simple question. You may have heard that in very cold countries, they sprinkle salt on icy roads, and somehow the ice begins to melt. But how is that possible if the temperature is still below zero? Well, this little mystery is exactly what we are going to solve today.
Here is our roadmap for today. We'll start with that melting ice mystery, then we'll uncover the main rule behind it. We'll use a simple analogy to help you remember, see what's actually happening to the molecules, explore some powerful applications, and finally, we'll wrap up with the key points for your exam. It's a very clear path.
So see, this very simple everyday observation about melting ice is actually our doorway to understanding a really fundamental principle in chemistry. And here is the secret. It's all about a special set of properties that have a peculiar rule. They don't care what substance you're adding. It could be salt, it could be sugar. They only care about one thing: how much you are adding. It's all about the number of particles, you see, the quantity, not the quality.
So let's give this idea a proper name. This particle count rule is really the heart and soul of colligative properties. If you can just grasp this one single idea, believe me, the entire topic will become very, very easy for you.
And for your exams, here is the perfect definition you should remember. Colligative properties are the physical properties of solutions that depend only on the number of dissolved solute particles, which is their concentration, and not on the chemical identity of those particles. The key thing to remember is it's the count that matters.
Now, there are four main colligative properties you need to know about. There's vapor pressure lowering, boiling point elevation, freezing point depression, which is the one that explains our salt and ice mystery, and finally, osmotic pressure. And you know what's amazing? All four of these different effects actually happen for the exact same reason. When you add solute particles, they simply get in the way and disrupt the normal behavior of the solvent. Now, this is a point where students often get confused. It is very easy to think that the type of solute matters, but it really doesn't. Whether you dissolve salt or sugar or some other non-volatile substance, the change in the boiling point or freezing point depends only on how many particles you've dissolved. Please remember that.
Okay, I know this idea of particles causing disruption can sound a little abstract. So to make it stick in your mind, let's use a very simple and memorable analogy.
I want you to imagine a swimming pool in winter. If the pool is empty, the water can easily freeze into a nice, smooth, orderly sheet of ice at 0 degrees Celsius, right? But now, just imagine that the pool is full of swimmers, all moving around. These swimmers are just like our solute particles. They are constantly getting in the way, making it much, much harder for the water molecules to line up and form that perfect ice crystal. And this analogy works perfectly. Let's map it out. The swimmers in the pool, well, those are our solute particles, like the salt ions. The swimmers disrupting ice formation is just like the solute particles disrupting the solvent's crystal structure. The more swimmers you have, the more disruption there is, which in chemistry means a higher concentration leads to a bigger effect. And finally, does it matter if the swimmers are tall or short or what they are wearing? No. In the same way, the chemical identity of the solutes just doesn't matter. Okay, that analogy is a great way to remember the concept. But now, let's become proper chemists for a moment and see what is actually happening at the molecular level. Let's build a clear mental image of this freezing point depression. So first, let's picture pure water. When you cool it down to its freezing point, which is 0 degrees Celsius, the H2O molecules slow down and start arranging themselves into a very specific and orderly hexagonal structure. This is how an ice crystal is formed. But now see what happens when we add salt. The salt, NaCl, breaks apart into sodium ions, Na+, and chloride ions, Cl-. These ions are now floating around, mixed in with all the water molecules. They are attracted to the water molecules, and they physically block them, preventing them from easily joining the growing ice crystal. They just get in the way. Now, because of this constant interference, this constant disruption from all the solute particles, the normal freezing process is disturbed. So to overcome all this chaos and force the water molecules to finally lock into their crystal structure, you have to remove even more heat. You have to make the solution much, much colder. This lowering of the freezing temperature, that is exactly what we call freezing point depression.
So you see, this is not just some interesting theory. Colligative properties have some incredibly powerful and practical applications. One is something you see in everyday life, and the other is, well, it's almost like a chemical superpower. Let's start with the one you might already know. Have you heard of antifreeze in a car's engine? Well, antifreeze is nothing but a solute, usually a chemical called ethylene glycol, that's mixed with the water in the car's radiator. By dissolving this solute, we are deliberately causing freezing point depression. And look at how powerful this effect is. A typical 50-50 mix of antifreeze and water will not freeze until the temperature drops all the way to minus 37 degrees Celsius. This is what protects the car's engine from cracking during severe winters. It's a direct, life-saving application of this very principle. Now, for that chemical superpower. For a chemist, the most important application of this principle is to figure out the molar mass of a completely unknown substance. Just think about that for a second. We can use these properties to effectively weigh molecules that are so tiny we could never ever see them. It is an incredibly clever and useful technique. And the process itself is very logical. It happens in 3 steps. First, you measure. You take a known weight of your unknown substance and dissolve it in a known weight of a solvent. Then you very carefully measure the change in the freezing point, which we call delta TF. Second, you calculate. You use the simple formula delta TF equals KF times M. Now, KF is a known constant, and you just measured delta TF, so you can easily calculate M, which is the molality. And finally, you determine. Since you now know the molality, and you know the masses you started with, you can simply work backwards to calculate the molar mass of your unknown substance. It's a beautiful way to apply theory in the lab. Okay, we've covered quite a bit of ground. So let's wrap this up by summarizing the most critical points that you absolutely must remember for your exams. This is your final revision. I want you to lock just 3 things in your mind. Number 1, the core idea. It is always about the number of particles, never their identity. Number 2, the mental picture. Just remember those swimmers in the pool getting in the way of the ice. It's the perfect analogy. And number 3, the application. Think of antifreeze protecting a car and chemists being able to weigh unseen molecules.
And that is our explainer on colligative properties. I can promise you, if you just walk into your exam holding on to that one core idea, that one mental picture, and that one real-world example, this topic will feel much, much lighter. All the very best.